Hello everyone, my name is Riddhimaan. I am in 8th grade. I am from Mason Middle School, and this is my project on harnessing the breeze, maximizing wind turbine efficiency. So our world has many problems. One of the most major issues happening right now to our planet is climate change. However, renewable energy solutions address climate change. There are many renewable energy solutions, but wind energy is the best because it is the most renewable and it is clean. So the question we can ask ourselves is, how do we maximize power output from wind turbines? So there are many benefits of wind turbines. So first, let's talk about environmental benefits. Wind energy is one of the most environmentally friendly sources of power with no air pollution, greenhouse gases, or toxic waste. By optimizing wind turbine efficiency, we can reduce our reliance on fossil fuels and lowering carbon footprints. There's economic advantages, which is when more efficient wind turbines can generate more electricity at a lower cost per unit of energy produced. Lower costs also make wind power more accessible to a broader range of markets and regions, potentially leading to significant economic growth in the renewable energy sector. The third thing is energy security. Diversifying energy sources by increasing the share of wind energy reduces dependency on imported fossil fuels, enhancing national energy security. The fourth, by making wind turbines more efficient, we can generate more power from a smaller number of turbines. This efficient use of space is particularly important in densely populated areas. The fifth thing is increasing energy demands. Global energy demand continues to rise. Wind energy, being both sustainable and scalable, is essential for meeting these increasing demands without exacerbating climate change. The sixth thing is technological innovation and job creation. Focusing on improving wind turbine efficiency drives technological innovation, leading to the development of new materials design and manufacturing processes. It's not only the field of renewable energy, but also creates high-quality jobs in research, energy, engineering, manufacturing, and maintenance. So the problem statement is that this science project seeks to investigate how various factors such as the angle of the blades, the number of the blades, and the length of the blades affect the power output of a wind turbine. Identifying the optimal configuration of these variables could significantly enhance the performance of wind turbines, contributing to more efficient wind energy harnessing and the production of cleaner energy. So what I hypothesize is that there exists an optimal angle, number, and length of blades that maximizes the turbine's efficiency in converting wind into energy. So it is predicted that a certain blade angle will be more effective in capturing wind, resulting in higher power output. So what I thought is that the 90-degree angle, it would generate the most wind power. There would be an optimal number of blades that balance between enough surface area to capture wind and minimal drag resistance. A specific blade length will optimize the balance between capturing sufficient wind and maintaining structural stability and efficiency. This will guide the experimental design, allowing for the testing and analysis of each variable affects the wind turbine's power output. So these are my materials and equipment, which was 2 different types of wind turbine kits, a ruler, a pencil and eraser, a stopwatch, a Sharpie to mark the wind blades for our rotations per minute. So when the wind turbine would spin, I would mark one of the blades, and whenever it would touch the pole, that would be 1 rotation per minute. A constant wind source, so in my scenario, I used a leaf blower, a control environment, and a timer. First thing I did is I constructed the 2 scaled wind turbines with turbine 1 with a blade length of 35.1 centimeters and turbine 2 with a blade length of 19.4 centimeters. Then I placed the first wind turbine in a controlled environment using a constant wind source. I recorded the rotations per minute of the wind turbine because I got the wind turbine to its maximum speed, and then I did this. I also recorded the time it takes for the motor to spin before it comes to a full stop inside the wind turbine. Then I repeated steps 2 to 3, 5 times for all angles of the turbine. The next thing I did is I removed 1 blade from the turbine. For 1 angle of the wind turbine, I recorded the rotations per minute of the wind turbine. I also recorded the time it takes for the motor to spin before it comes to a full stop. I then repeated steps 2 to 3 in the section 5 times for all angles. The next thing I did is I collected the data for the second wind turbine, in which I placed it in the same place in the same controlled environment with the same constant wind source, and I recorded the rotations per minute for 5 different runs of the turbine. So This is my data for the first wind turbine with 3 blades, and according to the data, it shows that between angles 30 to 60 degrees, the wind turbine was generating the maximum rotations per minute and the time for the motor to spin before it comes to a full stop in milliseconds. As you can see on the graph, at 60 degrees, the wind turbine was generating a rotations per minute of 49.4 and a rotations per minute of 20,032. The lowest one was at 0 degrees, in which the rotations per minute and the milliseconds was both 0. For the 2 blades data, it also showed that at between angles 30 degrees and 60 degrees, the wind turbine was generating the highest power output. As you can see on the graph, it was showed that at 60 degrees, the rotations per minute of the wind turbine was 49.4, and the time it takes for the motor to spin before it comes to a full stop in milliseconds was 18,274.6. So for the second wind turbine, since there was only one angular position of 60 degrees, the average rotations per minute was 87 rotations per minute. And as you can see, it spun much faster than the first and second wind turbine. So how does this relate to the power? So this is called the power equation, and there are 2 very important factors that impact the power output, the power equation, which is the swept area and the power coefficient. So the swept area is calculated using the formula for the area of a circle, which is pi times the radius squared, where r is the radius of the turbine blade, which is half of the blade length. The power coefficient is a dimensionless number that represents the efficiency of the turbine in converting the wind's kinetic energy into mechanical energy. It depends on factors like the blade design, angle of attack, and the rotational speed of the blades. The Betz limit, which is a theoretical maximum, dictates that no turbine can capture more than 59.3% of the kinetic energy in wind, but actual turbines typically have power coefficient values ranging from 0.35 to 0.45. So the swept area and the blade angle affect the power coefficient by influencing the turbine's ability to adapt to varying wind conditions and to operate efficiently over a range of wind speeds. So the swept area of the turbine with the blade length of 35.1 centimeters is approximately 0.0968 square meters, while the swept area of the turbine with a blade length of 19.4 centimeters is approximately 0.296 square meters. This shows that the first turbine with a blade length of 35.1 centimeters can potentially capture about 3.27 times more power than the second turbine with a blade length of 19.4 centimeters, assuming that all factors were equal. Since the power coefficient is a measure of the efficiency of the turbine in converting the kinetic energy of the wind to mechanical energy, it is influenced by factors like the tip speed ratio and the design of the blades. And this is calculated as the ratio of the blade tip speed to the wind tip speed. For the first turbine with a blade length of 35.1 centimeters, the tip speed ratio is 0.147. For the second turbine with a blade length of 19.4 centimeters, the tip speed ratio is 0.175. This means that the second wind turbine was spinning faster than the first turbine, but how the relationship between tip speed ratio and power is not linear and depends heavily on the turbine's specific design. The choice of the number of blades in the wind turbine design is a balance between aerodynamic efficiency, startup wind speed, rotational speed, stability, and power output. So in our control experiment scenario, it showed that the 3-blade turbine performed better than the 2-blade turbine. Modern large-scale turbines typically use 3 blades as a compromise between the above-mentioned factors. Next, let's talk about the angle. The blade angle, or pitch angle, which is the angle between the blade's chord line and the plane of the rotor of a wind turbine, plays a crucial role in controlling its power output and operational efficiency. So according to our experiment, it showed that angular positions of 30 degrees and 60 degrees showed the highest efficiency. So in summary, while the formula for wind power generation primarily depends on wind speed and swept area, the efficiency and performance of a turbine are significantly influenced by these three important factors, which is blade length, number of blades, swept area, and blade angles. So these are some of the pictures that I took during my experiment. This is my bibliography, so some of the sources that I collected from is Science Buddies, Learning Center, juliantrublin.com, and all science fair projects. If you have any questions, you can contact me at my email, which is riddhimaan.das48@gmail.com. Thank you.